Hi everyone, welcome to 365. So today I will finalize the cryptography module. The due maybe tomorrow, and Thursday we will start the access control module. So access control has only 2 weeks, two class, one for 1 week. So that's our current plan. Okay, let's do the following last class. Uh, so we, as a PKI algorithm, so we covered the RSI, the cryptography algorithm. So how to generate the key first, and using the public key, we can encrypt our message, and then the receiver they can the somebody can no only the owner of the secret key can decrypt that encrypted message with a public key. So that way can be used in the digital signature or securely transmissions environment. So following the last class, we will cover the hash functions today, and I will show you some demo for the remaining the challenges. So the hashing functions, we have to talk about the message integrity. What is integrity? I send some message to you, so can you trust the message is not altered during the transmissions and manipulated by any unauthorized malicious actor? So yes, if I wanna give you the trust, I have to show this message is not altered, modified. So that's the same as I sent with the origin message. So if some attacker flip a 1 bit of my message, what happened? So that message cannot be matched uh, with I sent the message, right? So how can the receiver know? Yes, so hash functions can provide about these questions. The first one is a cryptography hash functions, and also message authentication code, digital signatures. So last class in LCA, we learned the PK public key can be used for authentications, right? And the authenticity also, you are the true sender like that. So using the signatures. So that's the integrity, the another the features provided by digital signature or checksums. So checksum in data network data communications, I send some value, calculate the message I sent, and then include that value in the message. If the receiver got that message, he also, in the same way, calculate the message and match that result. In that way, oh, this message is not altered by matching the checksum value, but it has some fault, the weakness, right? If kept intercepted by the third party malicious user, he can manipulate the checksum value too. So that is the weakness of the checksum. So by comparing like this, commonly they compute some value with some expected value provide with the messages. So this is the way how can the receiver the has the convince this is the perfect 100% original messages. So cryptography hash functions like a specific the math formula. So it takes some data to give it the big or small, the turn into some a string of bits. Okay, like a sequence of 0 and 1. So the hash functions that maps that arbitrary size data to fixed size with a string. So what's that mean? Let's figure this. So when I input the 20-letter password, hash functions, for example MD5, produce the 1 to 8 bit digest. How about the 20 megabyte file, PDF file, that also produce the same size of the output, 1 to 8 bit digest. 1 terabyte hard disk, yeah, it also same the output 1 to 8 bit digest. Like that, hash function make the fixed size of bit streams. And also it has the very critical features. We call that one-wayness or one-way functions. What does it mean, one-way functions? So we call that irreversibility. So there are infinite input space, and that can be fixed throughout the hash functions, right? So that output can be relatively small, uh, comparing the output space. So one-way function means it is impossible to calculate the m message m from these output functions and function of m, right? So you cannot figure out what is the original message based on the output hash value. So we call that one-way features or irreversibility. Why it is very critical? Because the uniqueness of the message, we can use that as an identity, right? Here we can make our own hash value, and we can map that hash value. That's A, that's a B, that's a C. So each hash value can be mapped with a specific identity. So we can identify that specific one based on the hash value. Why? The hash value cannot be collision. The hash value cannot be produced the redundant value with against the different input. Like that, uh, hash function can have these very special the features in cryptographic hash functions. So the fixed size output and one-way functions is the compute and how to go back. So I guess you may use the hash functions. So hash functions, they produce the output very quickly, very quickly. There's very minor differences between very small, tiny input and huge input. So that's the great features why we use that hash functions for identify uh, some object or the files or images. So because it is very nice to compute quickly to the to for the output. Okay, it is a one-to-one mapping. So I emphasize there is no collisions in hash functions, but that is the theoretical goal of hash functions. But sometimes in some hash function, they produce the collisions, the redundant output. So like MD5, there's a very simple, basic, simple hash functions. So they are vulnerable to some the collisions attacks. So MD5 is not anymore recommended to use in our real life. Okay, and deterministic. So same input should produce the same output, and small change in input that make the completely change the output. Uh, it it sounds like the avalanche effect. So only one bit change, but the output the that we cannot figure out. Only minor changes are there. So that is the feature of the hash functions. So public key cryptography used to be the computationally very expensive. So hash functions used instead of public key cryptography, like in these scenarios. So Alice, um, we need to make a statement M. Everyone knows is from Alice. So M written by Alice. So Alice, she wanted to make the hash of that message M, the statement M, and encrypt with his her security key A, right? And send this signature. The signature means here uh, encrypted the output of hash value. Okay. In the real world, the signature we use the pen, right? And we put our initials or our the specific figures. But in the cryptography, the signing just the encrypting with a secret key. Okay. So here, this is the signing actions. So signing with secret key of Alice and send or the publish this message and the signed the signature. It means yeah, this message is author is the owner of this signature. How can decrypt? How can we verify the signature is from some specific, in this case, from Alice? So Bob calculate the message M in the same algorithm with Alice, and then the compare by using the public key of Alice against the signature the M. What does that mean? The public key that means the decrypt, right? So decrypt with the public key of Alice, the signature M. It shows the signature M, right? So if that output matches with this hash M value, so Bob can verify, oh, this message from Alice. In this way, this is the in the last class. You remember maybe like a non-repudiations and authenticity. So RSI, like RSI algorithm, they provide these features, and also we can do this uh, the using the message. The level is the hash values as a messages in the signature like this. Okay. So what if Eve alters M to M prime? So in this case, Bob can hash value M prime and compare with this publicly announced signature. So there will not be matched, right? Because the message is altered. So in this way, so they can check the integrity based on the signature of the message. Any questions? Also, the hash functions can uh, can be used uh, for the integrity of files and messages. And how about the password verifications? The Linux or Unix systems, they save the hash value of the password on a local disk, right? But they added some sort value, the random value, to avoid the predictions or dictionary attacks. Anyway, the password verification also, they use these hash functions. And proof of work. What is the proof of work? Have you ever heard proof of work? Where is it from? Proof of work. So blockchain terms, right? So uh, the blockchain is a very specific. The uses they have some specific rules how to add the new block in the blockchain network. So in order to if you like to add the new blocks, you have to solve. Actually, that is to predict the very long the value of nonce. So nonce is a random value. Start with some specific prefix, the number of zeros. So if you predict the hash value, you can add the new blocks like that. The irreversibility of the hash functions is very hard to figure out the input, right? So using that features in the blockchain, they adopt the hash functions for the proof of work to add a new block in the blockchain. And the file data identifier. So I teach the digital forensics. So in digital forensics, if we copy the hard disk, we have to produce the hash value of that hard disk images. It guarantees the original copy by matching the hash value from the hard disk. Like that, that is also can be used as a file or identifier. Okay. Here, three hash function properties. It's like some requirement of the designing hash functions. Hash function should meet this requirement regarding the resistance. What is the resistance? The first one, pre-image resistance. So if you have the value h, it should be difficult to find m, the input m, right? So I have an output value, but it is very difficult to figure out the input value. So we call that the pre-image resistance. Okay, that is the first character for designing the hash functions. So this is a requirement, first requirement. Second pre-image resistance. Okay, so we have another one, input M1, but it should be difficult to find M2 such that the same result, same output of that value. Okay? So we can get actually the hash value are publicly open normally, but they don't care. They don't make it matter because irreversibility of hash functions. Okay, so we can get sometimes we can get the input m, but we cannot find the m2 to make the same output. So that is a collision, right? So hash function should not have the collisions output. And third one, collision resistance. So the second pre-image resistance, sometimes we call that the weak collision. And the last one, collision resistance, the resistance, we call that strong resistance. So it should be difficult to find two message M1, M2 make the same result. It's a little bit similar to the second pre-image resistance, but we know in the third one, M1 and M2, so they cannot produce the same output. In the second pre-image resistance, we only know M1, but in the third one, we know M1 and 2. So that's the reason why you call that the second is a weak collision resistance, and last one strong collision resistance. Okay, so you have to keep this requirement to design hash functions. Okay, let's back to public key. So what is the weakness of the public key weakness? So public key, so they keep pairs, right? Public key and private key. So how to trust the public key? So everyone must uh, let others know his public key or her public key to decrypt or verify my signature or my messages, right? How to distribute that public key? How to trust that public key? Can you believe without any process? So that is the traditional questions. So let's see um, these scenarios. So if normally, usually Eve is malicious actor, evil like evil. So if replace the old public key with their own, how to that? So Alice try to uh, the encrypt with public key or uh, Alice Alice receive the or the Alice can uh, reach out this public key of Alice because public key is public, right? So anyone can access. So Alice can access public key of Eve and encrypt that encrypt the message with his the Eve's public key. That is the ciphertext 1 C1, and Eve intercept the message and decrypt with his own secret key. It is possible, right? Because the Alice used his uh, public key, so I can decrypt that with my secret key here. So I can get the original message M1. So yeah, this M should be M1, right? This M1. And in this step, Eve can change the M1 into M2, like the manipulations, alterations here, and make the ciphertext 2 using the P bits, the public key of B, the Bob. Possible, right? And Bob received this C2 and tried to decrypt with his secret key and get M2. So what do you think about this? It is possible, right? So we call this man-in-the-middle attacks. So public key could be manipulated like in this way by the man-in-the-middle attack. Okay, how can we avoid this? How to trust public key? The first one, delegate centralizations like a PKI. This is the ecosystems of PK, the creations of PK and also termination of PK. Like that, they manage the life cycle of the public key. We call that PKI, public key infrastructures. That is the one solutions. So this is the hierarchy of the key. So in the PKI, um, so the top authority we call that root to CA, and the middle we call that intermediate CA, and then the issuing CA. This is kind of some structure of organizations. So they are managed well, but it is the centralized management, right? So in order to issuing the certificate, so they have to communicate with this issuing share. Issuing share must be certified by this intermediate CA. Intermediate CA should be certified by the root CA. It's like a trust chain. In this way, we can trust that the public key, if they suggest, provide the who is your issuer. So my issuer is the CA here, and my certificate this one. So I can get verifications using both value. So in this PKI, they also provide some validations process. Like if you uh, if you need the transcript to apply some other university or company, but how can they, the company or other university, verify your transcript? They can call, or if there's some the QR code or barcode, so they can use that for verifying your transcript. It is genuine or not. In this way, this is the like that ecosystems, the verifying ecosystem. Okay. Reversely, is decentralized approach. So one of them is the web trust. So let's uh, get back down here. So PKI, what is the CA? So that's short for Certificate Authority. So only this authority issue the certificate to the requester, okay, responsible verifying identity, and can delegate to other trust CAs, creating the hierarchy. As you can see, there is the intermediate CA, right? The root CA delegate this authority to the intermediate CA. And also intermediate CA, they can delegate the control to the issuing CA. In this way, delegate to other trusted CAs that create a hierarchy or kinds of governance. Okay. So the goal of security, issuing revocations. What is a revocation? If you graduate ASU, that's your goal, right? After graduating, so ASU should revoke your credentials, like yeah, ASU ID or emails ID, like that. So revocation in terms of cybersecurity is very, very important, right? It's the basic PKI uh, descriptions. In the modern web, so PKI is well deployed and widely deployed. So one of the main product is HTTPS. So secure HTTP. So you may know, I guess you already know, how can we do that? So you can see here this lock icon, right? So it indicates this website provide based on the SSL protocol HTTPS. HTTPS, okay, based on the TLS and SSL. So you can PKI. So can we see the PKI here, public key? So well, signature, a certificate. So it's connection secure. So you are securely connected. This verified by let's encrypt more information. So here, so general informations print. with a site identity, and it has encrypted with this cryptography set, right? And view certificate here. Yes, this is a certificate used in SSL, HTTPS. Issue name. Yeah, this is the CA, the country US, and let's encrypt. This is the issuer for ASE website. Validity. It is kind of expiration date of the certificate. And subject names, the public information used algorithm RSA, right? We learned key size 248, 2048, and modulus exponent. The int. So this is the integrity information. So using the hashing algorithm SHA-256 and SHA-1 value, subject ID. Okay. So this is the another certificate, IS3, and another one. So this is the HTTPS, the example, and root CA. I already. So in TLS or SSLS, in the webs, the root CA must be displayed in OS and software, and there is some different types of certifications. So like a domain level certificate and organization validation certificate, extended validation certificate. So yeah, there's some various types of certification. So the purpose of this certificate can be different on depends on what the system need. Yes, you can see the visual indicators of status. This is a lock icon, right? And sometimes the organization name like this is the defense.gov, an official website of United States government. Have you ever seen this? So if you visit one of the government, uh, so you can see this website, this mark, and like this Apple, the company name can be shown, Apple Inc. Okay, and it's the status of current, the secure, right? If you visit non-secure website, so the lock icon is unlocked. Okay, currently most website they use the HTTPS, right? Mm, yeah, this is the on non-SSL, non-HTTPS website uh, link. They are vulnerable. Mm, So these visual indicators so useful for helpful for users. Oh, this website is secure or non-secure. So based on this, we can trust the website. Okay. So to avoid visit the compromised website by the hacker or the phishing website, the one of the primary checking list. Uh, those are these visual indicators. You should check that these lock icons or the name of the company or organizations. So in a this decentralization's approach, so web of trust. What is the web of trust? So this decentralized approach establishing or propagating the trust between the individual users, okay, or the some in as you can see, they can choose the way like a direct trust or indirect trust. So they can open their public key and open their the signature. And if you like to call me, to contact me, you can use this public key, and I can decrypt that messages with my private key, the security key. In this way, they can choose the individually the users. So instead of relying on some root CA like issuing ecosystem, uh, this way the web of trust allows user to uh, the trust others based on their the personal judgment. So actually, there's no tight regulations or anything, but this way have some benefit in terms of distributed approach. Okay, so user can drive this trust relationships, and we can do uh, the verify personally what you want. Okay. So this they provide some flexibility or some more resilience. So if this guy is not working due to some unknown errors, so he can this guy can use other one to make the trust. So, so like this, the user can have more control over the trust in the network. So there's the philosophy of the trust. Okay. Okay. This list is a cryptography research related the breaking crypto, securing crypto, new types of crypto. You can uh, search each topics, and if you are interested, you can dig into that topics in this resource. With this resource, okay. So this is a one-line hash calculator. So let's use the SHA-256. So if I type these five characters, so you can see. So if I start with 59 and C5, and if I delete the 5, yeah, the message to change it totally changes. So you cannot trace or guess based on the output value for the predicting the input value. This is the uniformity or like a avalanche effect, and uh, so yeah, no matter what the size of the input value, they produce the same fixed size of value, right? Okay. So let's. So this site is a dictionary attack based the cracking site for the. Okay. Mm, here, let's maybe use the like A B C D E and hash. Yeah, this is the output, right? And using the hash value, try to crack here. Yeah. Interestingly, the hash value produce the input value, right? So how it is possible? What happened? Because the input value is very short, and also the ABCDE very easy to predict. So as I said, this site is based on the dictionary, word dictionary attack. So that means it has already a lot of password dictionary, and they convert that value into each hash value and try to match that dictionary with the input hash value. In that way, they try show this result. Okay, so that's the reason why you have to mix some special characters in your password and make them longer, maybe than 8 letters or 10 letters. Make sense? Okay, so let's see some challenge demo. Yes. So I covered the 5 6. I made the videos for you. Did you check that? No. Okay. In the level 7, yes, so RSA decrypt RSA encrypted script using provide public and private keys. Mm, oh, 6 sevens. I made videos, right? So from level 8, RSA encrypt secret using the provide prime vector n. So they provide the prime vector n and how to decrypt. To this, you need to uh, maybe let's see. Okay. Level 8. Yes, they provide. We have E and P and Q and script text. So in this challenge, you will decrypt the script with the key with RSA. You will be provided by this. Uh, so we need to back to the RSA algorithm, right? So there is a the formula to make the uh, some. So I think in the level 8, see RSA. Yeah, I slightly changed some symbol here. So choose two prime number PQ they are provide, right? And we can get this N by product of P and Q, right? And we can choose, uh, we can get the pi functions and can be product of these two factors, and then choose the E. E gonna be public exponent, right? They can be choose from 1, the less than the pi n, right? So the greatest common divisor, GCD, uh, equal 1. So to meet these equations, how can we get the E? So that is the E, and we can compute the D. This is the private exponent, right? Can be get with this the formula, and we can do this easily because yeah, that is the Euler formula. Eventually, we can get a P and S. N is E, and the two pairs N E is the public exponent. This is a security exponent. So, example. Okay. So let's see the two numbers, prime numbers. P is 5 and Q is 11 and N is 55. So we can get the pi functions, get 40, right? 5 minus 1, 11 minus 1 makes 40. The combined product of them. And ED, the congruent with this formula, they can be converted like that. ED minus 1 is K means start with 1, 2, 3, 4. That means the multiple of the pi n. So 40, 80, 120. So ED is equal like this 41, 81, 1 to 1. So among them, we have to choose E that is the less than pi n. So pi here, that is the 40, right? So um, if you choose E, uh, is a 3, E is a 3, so 3D and 41, 81, 121. So among these values, we can choose, we can get D is equal 27, right? So public key can be the N, the 55, 3, and private key can be the 55 and 27. So we can do this in a Python very easily here. So let's use Python, right? So import um, process POW. Okay, can do that. POW is, let's see, the message is 5, and here is the key. The 55 is a modulus, right? And 3 is a public exponent here. So I can type 3 and 55. It makes the 15, right? So we can also decrypt this 15, use the private exponent, the 27, right? And 55. Oh, no. Mm, yeah, 27. But, message is 5, 3, 15. Okay, let's leave it. Anyway, this is the way to decrypt the message in a RSA. Um, what is that? Oh, my mistake. Mistake. Why? 27, right? Yes, fine. So this input message decrypt here, the 5. Okay, in the same way. So you can use like a 20, makes it 25, and we can decrypt this 25. Yes, 20. So we can get this message input. In this way, in the RSA, this is the level maybe in the last class. In this way, you can get the message here. Okay, this is the base, right? And this is the exponent and the modulo n. So in the level 8, they provide yeah, they provide all parameters E, P, Q, right, and script. So in the algorithm, yeah, the P, Q, E, and the script message, they're gonna be this one. Secret message is like challenges. They are cipher text, right? So you need to uh, get this using this formula and get the D with provide the parameters. So we need to use the exclude Euclidean functions, and you can search that in the internet. You can get uh, the algorithm or code for that. So you have to implement this part to get a D in the level 8. Okay, so that's my hint. Okay, RSA. So this is the another the demo to get the D. So you can use the in this case this is the level maybe 9. Let's move to level 9. Find a small collision using SH256, the 2 byte, first 2 byte. So let's learn the challenge. Oh yeah, so there is only 2 byte input, right? Only 2 byte input. So input space very small. So we can try to brute force attack to match. They show the algorithm, and we can generate random input. So we only match the against these 2 byte input size. So it is not difficult because the input space is very small, and we already know the algorithm, and we can try to brute force attack. But we need to generate the keys using the crypto library in Python. So you have to use this import the crypto key from and import RSA, and this is the process. This is the generations of key. Okay, so what kinds of keys are generated here? So modulus n and public exponent e, right? And private exponent d, first prime number q, and second prime number p and q. So based on this, we can uh, make the formula, Euler formula, uh, to get the d to the this is the proposal text to find no. Oh, okay. So this is not the. This is the maybe in level 8. You can you can the level this code to create the keys, and yes, using the this library, so you can get actually 9.8 is a different story. So in this level, so we use the hash functions, right? So what is the hash functions? We use the hash library in Python input, and let's say this is the example input. In order to calculate, it will be encoded, and we can get this digest value. Let's run this code. 10. Show chat. Okay, you need to implement this one. First, let's get this value, SHA256. So key length is 64 bytes. And how about so I implement and the SHA-1 algorithm the same way. Yeah, but the key size the different, the 40 and that's one MD5. The key size is sorry, it's a typo. Yeah, 32 byte. So how to hash by input a value? So you can use this way. And to perform the brute force attacks, you need to use the random functions. How to use random? Import random library here. Okay, and you need to define the range from 0 to 100 here, and those are converted to the byte in order to input to these hash functions, and then they will be print out with a hex digit. So let's run this code. Hash random. So yeah, from 0 to 100, there's we got the 13 random value, and the hash value is like that. So you have to match this value, the first two byte uh, of the challenges. Let's see the challenge run again. Yeah, so you have to find out, make this produce uh, first two byte hash value using this random brute force attacks. Okay, that is the level 9. Okay, and let's move level 10. So compute a small probe work by appending response data to the challenge data, resulting in a SHA hash with 2 null bytes. So this is actually similar to the previous one, level 9. So just replace the first two byte with a null byte. Okay. Yeah. The challenge is like that, but I start with begin the 2 null byte. So you have to match the first two byte containing the null byte. Actually, in the blockchain, adding the block, so you have to find the hash value start with some number of zeros. So maybe it mimic that process. Okay, let's move. In the level 11, complete RSA challenge response using provide public and private key. So it confused me. The previous demo random. So let me see. Level 11 to see challenge run. So they also provide every key values E, D in RSA and N and challenges. Challenges are secret messages. So using this, we can make the response. Response is the secret message, right? Um, you can just understand if you are understanding the RSA algorithm. You can do with that formula or formula and how to get this D. This is the D with this given parameters. So I think it is not difficult for you to understand the RSA algorithm. So you can check the some run code to see how it works. Um, you can see like a less challenge or run and level 11. Yeah. So understand the challenges, you can use this way to interpret each line here. So they just uh, get this D value using a P or W. You can get the flags. Okay. And let's remove the 11, 12. Complete RSA challenge and response by providing the public key. I think maybe let's see. This challenge complete RSA challenge and response. So you will provide the public key. Yeah. So they do not provide any values or parameters, right? So you have to generate your own key pairs using the RSA algorithm. So this demo, what is it? RSA, oh yeah, hash random. No, no, RSA demo. Yeah. So you have to use this library to generate the RSA key pairs, key set, and EDFQ. If you generate this E, you have to send this value to this prompt, like send line, process library, and then you will get the response from the server, and you have to get the value, the D, uh, using these functions of POW, power model. Okay. Uh, let's run the challenges. Maybe Python RSA. So N. I generate N and E. This E is on the, we can get this D and P and Q. These are prime numbers for the first time and second time. So here I set the challenge as a 10, right? And challenge can be calculated with this response, right? So print response, yeah, 10 response like this, and there is the decrypt with these functions POW, the response, the exponent, and uh, n, and that makes the original text 10, right? So in this way, using the public key, the private key, these are private exponent, right? So encrypted. Maybe they can change it here. E, D. Yeah, it works. Okay, 10. So encrypt using the the public exponent and decrypt with the private exponent. Okay, so this is the way in the level 12. And last two modules, I think that is some a little bit difficult. Assign a user certificate using provide the self-signed root certificate and root privacy. So let's see. Yeah, due to the lack of time, so I draw. Um, so this is the flow chart I made for you in the level 13. So you have to generate RSA key first, and then send that some of the key materials to the process. Then you can get some response from the process and decode it and parse that JSON format and make the user certificate. Certificate is encryption with a private key, right? And define the signer as a root, and then send. This is the creations of this design process of user certificate, and encoded that. If you send that to the process, they will send the response. We just decrypt that messages and with your private key, so that will be shown. That is the plex. Um, okay, level 13 and level 14 also. That's a comprehensive. Everything's are in these challenges. If you have key exchange and RSA key generations and certifications and AES symmetric key generations, and then the signing process, the certificate. Lastly, they verify that certificate. In this way, you have to read the challenges as I shown. You can see the less challenging and run and level 14. Oh, level. Okay. level 13. Oh, okay. Uh, so, yeah, I strongly recommend to read the challenges by yeah the Beam or BI or any editor that wrote the challenge the slash long pipeline. So you can interpret the questions, and you can also following some coding method in the challenges. Okay. Thank you. Good luck. See you on Thursday.